So now we'll switch gears and move on to section 1.2, where we discuss elements and the structure of the atom. And we briefly mentioned the atom before. It's the smallest and most fundamental unit of matter. We cannot separate the atom into any parts and still have carbon, still have hydrogen. We can't still have matter if we separate the atom. And an element is a substance composed of one type of atom. So if we have pure gold, gold is an element. It's composed only of atoms of gold. A compound, on the other hand, is a substance containing two or more elements in specific ratios. For instance, water. Water's chemical formula is H2O, meaning it has two hydrogens and one oxygen for each water molecule. So it's a compound because it's composed of two or more elements. The parts of an atom, then, contain generally in the nucleus. The nucleus is at the center. It's very small compared to the whole atom, and it contains subatomic particles. Protons and neutrons reside in the nucleus. Protons have a charge of +1. They have a mass of 1 atomic mass unit. It's a very small unit of mass, and they're located in the nucleus. The neutrons are neutral. They have a charge of 0. They are about the same mass as a proton, 1 atomic mass unit. They also reside in the nucleus. The third subatomic particle is called an electron. It has a negative charge. It is much, much smaller than a proton or a neutron. We can see this value here is much less than 1. And they do not reside in the nucleus. They are located in orbitals surrounding the nucleus, much like the planets orbit the sun. Not exactly like that, but that's a good representation at this point. In terms of size, if we have a football at the center of this football stadium, that could be considered the nucleus, and the electrons would be in orbitals in these nosebleed seats in the way back. So we can see that the nucleus is a very small part of the atom. It contains most of the mass, but the electrons are relatively far away from the nucleus. And electrons occupy orbitals, which are regions of space outside the nucleus. A freshman chemistry course for science majors would contain a much deeper discussion of orbitals, but in our case, we can understand that orbitals can take on a few different shapes. For instance, what's called an s orbital is a spherical shaped orbital. What's called a 2p orbital essentially looks like a dumbbell, something you'd use in weightlifting. It has two lobes, one on either side of the center of the atom. And electrons don't travel exactly on the surface of this orbital. They're contained within the area in the volume of that sphere, or the volume of these two lobes. And so they occupy regions like a cloud, not just the surface of the orbital. And so here, if this was an s orbital, a spherical orbital, the electron could be anywhere in here, much like air in a basketball. It is located within the entire volume of that basketball. It's not just on the surface of the basketball. We can discuss atomic mass in terms of the mass of the protons and neutrons. Most of the mass of an atom is in the protons and neutrons, and that is in the very small nucleus. Each of these has 1 atomic mass unit of mass, which is a very, very small number of grams, 1.66 times 10 to the negative 24. When you work on the math review lab, you'll see that this value here is very small. There are many zeros in front of 166. And so the nucleus has nearly all the mass and only a very small volume, so its density is enormous. Remember that density is mass over volume. So if we have a large mass, small volume, we have a very high density. Clicker question 1.6. The electron blank the proton. Choose the best answer from these four. So it's much lighter than is a good answer. The electron is significantly lighter than the proton. Going back to this slide, we see that the electron has 0.00055 atomic mass units versus 1 for the proton and neutron. So it is much lighter than the proton. It doesn't have the same charge. Electron's negative, proton is plus. The electron does not orbit the proton. It surrounds the nucleus. And it's certainly not much heavier than the proton. So A is the best answer in this case. So now we can learn about atomic number in respect to describing different elements. So the atomic number is the number of protons in each nucleus, and it identifies each element. If you look at the periodic table in the inside cover of your hard copy of the text, or in your loose leaf text, or if you go to www.ptable.com, you can look at an interactive periodic table, and you'll see that each element has its own number. So if we say element number 15, that's different than element number 27. So each element has its very own number, and we can use that to describe the element. Also, atoms have overall charge neutrality. They have zero charge. And that means they have the same number of electrons, which are negatively charged, as they have protons. The number of neutrons might differ from atom to atom because those are zero charged. We could have 50 neutrons or 10. That doesn't affect the overall charge of the atom. This would affect, of course, atomic mass because neutrons have mass, but not the number. They don't have any different charges. So for example, the atomic number of carbon, C is the symbol, is 6. That tells us it has 6 protons. The atomic symbol is a 1 or 2 letter designation for each element. It's always uppercase, followed by potentially a lowercase letter. So most are the first 2 letters of the English name for the element. So Ca is calcium, He for helium. Some symbols are a little more strange. They're derived from their Latin names. So Fe stands for iron, Hg stands for mercury. So most elements, we derive their symbol from the first 2 letters of their name. Other times we derive their symbol from their Latin names. So when we describe elements, we can describe both physical properties and chemical properties. Physical properties are defined as properties that we can study without taking into account interaction with other substances. For example, color, hardness, density, and boiling point. We can observe these without watching that substance interact with other substances. And chemical properties, then, are properties in which we must take into account interaction with other substances. So, for instance, the reaction of oxygen with gasoline in a car engine, which causes explosions and moves the car forward, or the rusting of a nail. Iron doesn't just rust on its own, it reacts with the oxygen in the air. So physical properties, grass is green. I can stare out my window and see that the grass is green. It doesn't matter if the grass is reacting with anything or if it's changing, the grass is green. I can observe that water boils at 100 degrees Celsius or 212 degrees Fahrenheit. I don't have to take into account the interaction of water with any other substances. That's a physical property. On the other hand, food providing energy is an example of a chemical property. So I eat the food, it's changed into energy and heat and waste products. And so I know that the food has interacted with other substances because it becomes changed. So that's an example of a chemical property. Same thing with burning wood in my fireplace. I put the log in the fireplace, I light it on fire, I get heat and light from that wood, and eventually it turns into ash. It's different from the wood that I originally added to the fireplace. That's a chemical change. So we also want to define a term called isotopes. So atoms that have the same number of protons, but a different number of neutrons are called isotopes. They're the same element, but they're different isotopes of that element. Carbon has 3 isotopes. They all have the same atomic number. They all have the same number of protons because that's what defines carbon. It has 6 protons. However, they differ in the number of neutrons. One of them has 6 neutrons for a total mass of 12, 6 plus 6. One has 7 neutrons, total mass of 13. Another has 8 neutrons, total mass of 14. Some isotopes are naturally occurring, and some chemists can make in a laboratory, so they are artificial. So as we saw, the mass number of the isotopes is the sum of the protons and neutrons, and the mass number is written as a superscript to the left of the symbol. Here's the mass number for carbon-13. The atomic number, 6, is always the atomic number for carbon. It appears as a subscript to the left of the symbol. So this is the symbol for carbon-13. The total number of protons and neutrons, and the number of protons. So we see that given the symbol here, we can determine the number of neutrons present in this sample of carbon-13. There are 13 minus 6, 7 neutrons present. So the isotope symbol here, carbon-13, we can also write carbon-12 and carbon-14. All three again have the same mass number. The same atomic number, same number of protons. An alternative representation is just to write out carbon-12, carbon-13, carbon-14. So within a sample of an element, the atoms will have different masses due to the presence of isotopes. And so we can get an average atomic mass, which is a weighted average of the mass of the isotopes based on their natural abundance. And oftentimes we refer to average atomic mass simply as atomic mass, and that's the number reported on the periodic table. Okay, so a practice problem. Only one stable isotope of gold exists, and it contains 116 neutrons, 79 protons. Write this isotope using the element symbol with the atomic number and mass number in the conventional format. So, the element symbol of gold is Au, and its element number 79. It has 79 protons, so it's located on the just to the right of the bottom center part of the periodic table, element number 79. So we want to write this isotope using the element symbol with the atomic number and mass number in the conventional format. So here we write Au, atomic number always goes on the bottom, 79, and then the atomic mass is going to be the total of neutrons plus protons. 116 plus 79, 195. So let me write 195 up here. And that's the element symbol for this isotope of gold, gold 195. The atomic number 79, that tells us there are 79 protons, 79 electrons. The atomic mass, 195, tells us there are a total of 195 protons and neutrons in this gold sample. Clicker question 1.7. How many protons are there in nitrogen-15? And here's the alternative representation of the elemental symbol of nitrogen-15. So as we just got done discussing, the atomic number 7 tells us how many protons there are in the element. So don't get confused by the 15. That's the total number of protons and neutrons. There are 7 protons in nitrogen-15.